Question 3 asks us to find the inverse metric of the Minkowski space metric, as shown here. So we know that the inverse metric multiplied by the original metric will give us the identity matrix, or the Kronecker delta. And it's because of this we can set up a system of equations that will allow us to find the components of the inverse metric. Once you solve for A, B, C, and D, you'll find that the components of the inverse metric are the exact same as the original Minkowski metric, as shown here. If you think about what this metric actually does, if you consider how the original Minkowski space metric is going to take an upper index and lower it, the inverse is going to take a lower index and raise it back up. Question 3b asks us to consider the length of vector v. And so we see right here that we have component v1 squared plus v2 squared, and that's going to give us the squared length of v. And so if we set x equal to v1 and y equal to v2 in Euclidean space, we're going to get a circle here. This circle represents all the vectors with the same length. And so if we do this in Minkowski space, we're going to end up getting a hyperbola shape looking like this. Now, if the constant that this is equal to is an imaginary number, we're actually going to get an upward facing hyperbola, upward and downward facing, rather than leftward facing and rightward facing. Now, for the next part of the problem, it talks about how x can equal v1 and t can equal v0. And so this is special because this only makes sense if x and t are different signs. And so as you can see right here x is negative, t is positive, and here x is positive and t is negative. And so only this part of the plot is going to be there. This dotted line right here won't actually exist because of how it's defined in the Minkowski space. But still, it forms sort of I guess you could say a half hyperbola. Question 3c gives us the energy of a particle and asks us to prove a couple of things using this. And so the first thing that we're asked to show is that E equals mc squared when V equals 0. And so as you can see right here, P expresses momentum, and so P equals mv. And so as V goes to 0, well, P also equals 0. This means that E equals C times the square root of mc squared plus mv squared, where this term right here goes to 0, which just gives us C times mc squared, square root of that, so then mc squared. And as you can see, E does equal mc squared when V equals 0. And so for part 2, we now need to show that when V is far less than the speed of light, E equals mc squared plus a term 1/2 mv squared. And so we can do this using a Taylor expansion. So we can write this with respect to V squared. So the first term is going to be mc squared plus V times the partial derivative with respect to V squared of this expression right here. And as you can see, once we're done with our Taylor expansion, that we end up getting mc squared plus 1/2 mv squared. Question 3d gives us the Minkowski metric and asks us to show that the transformation leaves n Question 3d gives us the Minkowski metric and it asks us to show that the transformation, where it's modified by lambda right here, leaves eta invariant. And so that's shown right here. So the transpose of lambda times eta times lambda should give us the exact same metric. And so we can show this by just doing basic matrix multiplication. It's important to also mention that the transpose of lambda is actually itself. We can then write these hyperbolic functions in terms of e to the x, as shown by their definitions here. You can see that once we simplify, we actually end up getting the original metric. This proves that lambda is an invariant boost, which means that when it affects a quantity, such as this metric, it is unchanged by the Lorentz transformation, showing that it is invariant. Question 3e asks us to do the exact same thing, but with lambda equaling something a little different, as shown here. This gamma is equivalent to 1 over the square root of 1 minus beta squared. And so following a similar process to last time, we can write it out as follows. What we want it to be, with 1 here and negative 1 here, we can use the definition of gamma and plug it back into here to get the metric that we want. As you can see, the Lorentz transformation that lambda causes is invariant because the metric still remains the same even after the transformation.